In yesterday's lecture, we were looking at pH, and we looked at some different everyday chemicals and pH, and one of the things we talked about was acid rain. And I mentioned that there were several areas in the United States that had especially high levels of acid rain. And recall that we defined acid rain as rain which has a pH of less than 6. Normal rain already is slightly acidic, so when we say acid rain, of course, we're meaning that rain which is more acidic than normal. I did happen to find a graph of the acid rain in the United States, just again to reiterate a little bit as to the high areas of the country as far as acid rain is concerned. We see here that the West Coast is really not very acidic, and one might wonder with cities like Los Angeles, San Francisco, etc., why we don't see more acidity out there. They're very dry climates. And because of that, we don't have a lot of rainfall, we don't have a lot of acid rain, and we have very strong westerly winds. So most of the air pollution actually that is produced in those areas is actually precipitated out much more east than we would anticipate. We see that the central part of the country where, of course, we live is about average. We see that it's light yellow in color here, which indicates that we have pH of our acid rain. This is an average value for the year 1995. We have an average pH in our rain of about 4.8, something about that area. So it's definitely more acidic than just normal rainfall. Normal rainfall out in this area we see is 5.5, becoming a little more acidic as we move back towards our direction. Then we see that starting from there out to the eastern seaboard, of course, we have considerable difference in the pH. And we see that the real heavy areas, in other words, the most acidic rainfall, right in this area here that I was mentioning, the highly industrial areas, we see pHs of 4.3. Now again, that's an average for all of 1995. So obviously there were times when we had rainfall that was maybe a 5.8. We had other times when rainfall may have been in that 3.5, 3.6, 3.7 pH range. The other thing that I mentioned in the previous lecture was the concern of Canada about our air pollution, because quite obviously if you look at the darkest reddish brown area, it is right along this strip of the U.S.-Canadian border. And quite obviously the rain doesn't all fall on this side of the border. So the timberlands into Canada are quite concerned with what we're doing to the air quality in the United States. And we do have a joint commission between Canada and America that are looking for ways of helping decrease air pollution in the United States side to decrease then the acid rainfall on the Canada side. But again, as I say, these are the average pHs for the entire year, 1995. 1996, of course, we've just completed, so it will be about 6 months before that data is processed and we have a look at it. The other thing I should point out here, notice that there are 3 spots here in Missouri. Notice that the southeast corner of Missouri is certainly more acidic as far as rainfall than the western part. Again, if we think about it, we do have more industrial areas over there. We have some of the mining, lead mining areas, etc., that do have a fair amount of coal burning processes. And so we see a higher pH, a lower pH and more acid. And of course, if we look at the airflow patterns, which kind of come across the United States like this and then start back up, we're probably also seeing a contribution of such places as Little Rock, Arkansas, and even Memphis, moving up air into that area and the pollution falling out. So the air pollution doesn't always fall out where it is being produced. It can go considerable miles before we actually see the effect in the rainfall itself. So airflow patterns, etc., are important. Oh, as I started to say, we noticed 3 dots here in Missouri, and those are the collection sites. There were 4 dots. We used to operate one just out of Springfield, about 25 miles. For about 5 years we collected the data. However, it was not refunded, and so the site was taken down and is no longer in operation. But we still have a good scattering of sites throughout Missouri that collect rainfall on a weekly basis and then measure it in the field. That means that's what we're seeing here, measure the pH directly there when they get the sample. Then the sample is sent in and it is fully analyzed for other chemicals like nitrates, sodium, ammonium. So there are a whole bunch of chemical tests that are done on each of those samples of rainfall. So not only do we monitor pH, but we can monitor other chemicals as well. All right, well, let's turn next then to talk a little more about the quantitative calculations involved in working with pH. And we'll look at a couple more questions at the end of the chapter then. The next problem that I have to take a look at says that we have a solution whose pH is 10.64, and it asks the question, what is the hydroxide ion concentration? Now again, even though we've done so before, it probably would be useful to put together those things dealing with pH that we should recall. We recall that for an aqueous solution, hydronium ion times the hydroxide ion concentration, brackets means moles per liter, is equal to 1.0 times 10 to the minus 14. We also recall that pH is equal to minus log of the hydronium ion. And in a previous lecture, we also rearranged this so that we could talk about that the hydronium ion in a system, that's just rearranging this equation, hydronium ion is equal to the anti-log of a negative pH. Okay, in other words, we change the sign. It's not a negative pH, it's a positive number, but we make it negative before we carry out the mathematical function. So those are 3 relationships to keep in mind to talk about acidity or basicity then of aqueous solutions. In looking at this particular problem, we see that we're starting out with a pH. We want to find the hydroxide ion concentration. Well, if we look at it here, we could say, based on this, I could find the hydronium ion by using this equation here. Once I have found the hydronium ion, I can go up to my first relationship, which is the relationship between hydronium and hydroxide, and solve then for the hydroxide ion. So we have a couple of step process. First, we're going to have to determine what the hydronium ion is. Then using that, we will determine what the hydroxide ion is. So stepwise then, putting it in, where first thing we're going to have is hydronium ion is equal to the anti-log of minus 10.64. And plugging that into our calculator, as I indicated previously, there are 2 logic processes. Some calculators you must punch the function key first. More calculators go the other way. We put the number in first and then hit the function key. So in this particular one, what I would do on the type of calculator I have, which I'm using a Casio, I put in 10.64, and then I look for the little plus minus sign. So I make it minus 10.64 on the display. Now I look for a button which is the anti-log button. We don't normally see one that says anti-log on it. If we see a log button and then a little writing just above it, that usually means that the second function or the inverse function of the calculator is the anti-log. Or the button may have on it just 10 to the x. That's the anti-log. Because what we're really asking is to what power do we raise 10 to get this number. So if we now take on mine the inverse, which now, and then I go to the log button and I read my final number, which is 2.3 times 10 to the minus 11. Again, in terms of significant figures, even though this looks like we have 4 significant figures, remember in pH, only the numbers after the decimal are representative of significant figures. So pH at 10.64 has in it only 2 significant figures. Therefore, we can put only 2 significant figures in the hydronium concentration. All right, now that we've done the first step, we can now go to our relationship up here that relates hydronium to hydroxide and solve now for the hydroxide ion concentration. So our final step then will be hydroxide ion concentration is equal to 1.0 times 10 to the minus 14 divided by the hydronium ion concentration, algebraically rearranging the top equation. Plugging in the number then for the hydronium ion that we just calculated, and I'll just go ahead and write that right below it here, 2.3 times 10 to the minus 11. And then we will calculate what the hydroxide concentration is. So divide by 1 exponential minus 14. And we end up with a final answer then of 4.4 times 10 to the negative 4th. All right. Any question on any step of that? Now, we might also ask the question, did this solution up here represent an acid or a base? And of course, we can just look at our pH to determine that. What kind of system is it? Basic or acidic? Basic. Remember, if pH is greater than 7, we're talking about an acid. If pH is less than 7, we're talking about, oh, I said that incorrectly. If pH is greater than 7, we're talking about a base. If pH is less than 7, we're talking about an acid. Okay? All right. Well, with that in mind also, let's go ahead to another question here. This we're not going to do any calculating. We're just merely going to ask the question, is each of the following solutions then an acid or a base? Well, if we go down here, we can obviously pick out 2 real quick and answer them because they're expressed in pH, which makes it fairly easy. So if I look at this one right here, the pH of 5.4 is less than 7, and therefore we would determine that this is in fact an acid. The last one here, pH is 13, so therefore it is greater than 7, so therefore it is a base. So pH greater than 7, it's the base. And up here, pH less than 7, and so it's an acid. Now the other 2, then, we have a couple of choices. Of course, we could convert them into pH. That would be one way. But we also made a statement about hydronium ion relative to acidity and basicity. if you recall, we have stated that if the hydronium ion concentration, remember in pure water, it's 1 times 10 to the minus 7. So if it becomes an acid, it means we've added more hydronium ion, which means then for an acid, hydronium ion should be greater than 1.0 times 10 to the 7th. That is an acid. Well, if we look up here at our number for the first one then, we see 3.6 times 10 to the minus 9. And that is smaller than 10 to the minus 7. That is smaller than 10 to the minus 7, so therefore this is in fact a base. Now the last one, the hydroxide ion one, we would need to convert to either again a pH or a hydronium ion so that we could make our determination. Or we can also relate to the fact that the hydroxide ion concentration is equal to 1.0 times 10 to the minus 7 is neutral. If I get more hydroxide ion in the system, if I add some hydroxide ion, then it means that it has become basic. And so we can really make a statement here then that if the hydroxide ion concentration becomes greater than 1.0 times 10 to the minus 7, we are talking about a base. Remember, the two are in equal amounts in water, and what we're doing when we add an acid or a base is we're increasing one or the other. And as we increase one, the other has to go down. All right? So, if the hydroxide is greater than that, it is a base. We look at here at our number, 3.0 times 10 to the minus 7. Is that bigger than 1 times 10 to the minus 7? Yes, it's 3 times bigger. So therefore, seeing that it is larger, then this means that this is in fact a base. The alternate choice would have been to convert from hydroxide to hydronium and looked at this relationship, the hydronium ion. If we do that, and I can just plug this in real quick, the hydronium ion would be 1 times 10 to the minus 14 divided by 3 times 10 to the minus 7. So I'll just do that quickly. 1 times 10 to the minus 14 divided by 3 times 10 to the minus 7. The hydronium ion, in this right here, the hydronium ion is equal to 3.3 times 10 to the minus 8. Now, if I looked at that, that would tell me that I have a hydronium ion less than 1 times 10 to the minus 7. Therefore, it tells us that the system is basic. So either looking at the hydroxide or looking at the hydronium, of course, gives us the same answer to the question. All right, any questions on any part of that one? Okay. Now, the last part of the chapter deals with stoichiometry involving acid-base reactions. And we sometimes refer to this as a titration. A titration is involving a solution in a stoichiometric reaction. Okay, so we're going to use our balanced equation. We're going to be working with a solution of either an acid or a base, and make some quantitative calculations. We refer to that as a titration. Now, to carry out a titration, if we're reacting, let's say, two solutions, a solution of an acid and a solution of a base, as a matter of fact, we had a sample of acid and base down here in a previous lecture. As a matter of fact, we have it here again. But if you notice, both the acid and the base are colorless solutions. How do I know when I've added the correct amount of acid to base to neutralize it? How do I know when the reaction has been completed that I can record data and make calculations? Well, we have to have some way of knowing when we reach that. One way is to use a pH meter. If we use a pH meter, we can then carry out the acid-base reaction, watch the pH meter till it gets to a pH of 7, which means that we've neutralized the acid or the base, and take our readings and make our calculation. The other way, of course, is to use an indicator. In a previous lecture, we looked at how indicators behave. They're materials which change color as we change acidity, change pH, and we looked at one called the universal indicator that went through a series of changes in colors. But we often just choose an indicator that just makes one color change. One of the ones that is most commonly used is an indicator called phenolphthalein. And phenolphthalein as an indicator, when we put it into an acid system, a system with a pH greater than 7, pH greater, I'll get this right, a pH less than 7, is colorless. When the pH of the solution becomes basic, greater than 7, the phenolphthalein turns to a reddish color. So by watching the indicator, we can then tell when we have neutralized the acid, because the solution will begin turning red or pink in color. Here we see that we're adding now some base to an acid solution, and we see a little bit of the pink color showing up. Usually this will show up, and then as we swirl in the titration, it disappears for a while, until finally we reach the point where we in fact do have a permanent pink color. Once we have the permanent pink color, this is the way we started, that's our acid. This is the color after the indicator has changed color, meaning that we now have neutralized the acid. At that point, we can stop and take our volume readings for our acid and our volume readings for our base, and we can make quantitative or stoichiometric calculations. For those of you that are doing the laboratory part of this course, one of the experiments that you will be doing is to do an acid-base titration. You will be using phenolphthalein in the lab to look at this color change. We can go either way. This case, I'm showing that we're starting with an acid and we're titrating with a base until it becomes pink. We could start with the base and put the indicator in, which would be pink, and add acid to it until it became colorless. Either way, we have neutralization of one or the other, and we have the information needed to make our calculation. Well, let's take a look now at a couple of calculations then involving an acid-base titration system. The first one I have here is the reaction between the base, lithium hydroxide, and the acid, arsenic acid. It gives us the information that we started with 50 milliliters of the acid. We put it into a flask, just like shown in the previous slide. And we put some indicator into it, like phenolphthalein, and it's colorless. We begin adding lithium hydroxide, that's the base. And we find that when the color finally occurred, when we finally know that the reaction is done, we have used up 116 milliliters of the lithium hydroxide. We know what the concentration was. That's called our standard solution. Our standard solution is the one that we know the concentration, and we're going to use the standard solution to determine the concentration of the other. So it had a concentration of 0.382 moles per liter. What we want to know is, and that should be really an uppercase M here, not a lowercase m, we want to know the molarity of the acid in this titration. Now, again, we follow the steps of stoichiometry. The first step is to determine the number of moles of known substance. Our known substance is the base, the lithium hydroxide. So the first thing I want to do is calculate the number of moles of lithium hydroxide. So moles of LiOH are equal to the volume expressed in liters, 0.116 liters, multiplied by the concentration in molarity, 0.382 moles of LiOH per liter. Remember, we said in the chapter on solutions that if we multiply the volume of solution times its molarity, we have the number of moles of solute. So the liters will cancel. We're going to end up with moles of lithium hydroxide. And let's see, we'll get a number for that here. So we have 0.116 times 0.382, and we have 0.0443 moles of LiOH. Step number one, determine the number of moles of known. Step number two, determine the number of moles of unknown, H3ASO4. That's going to be the number of moles of known multiplied by, remember the second step always involves the stoichiometric relationship from the balanced equation. So our second step then is going to be to multiply by 1 mole of H3ASO4 per 3 moles of lithium hydroxide. We get that from our balanced chemical equation at the top. Notice our units, moles of lithium hydroxide, cancel, and we then end up with a number at this point of, let's see, divide by 3. So we end up with 0.0148 moles of H3ASO4. 2/3 of the way done. The third step, solve for whatever units it is that we want. In this case, we want to find the molarity of the acid. What is molarity by definition? It is the number of moles of solute, in this case the acid, per liter of solution. Now we have just calculated the number of moles of acid, and we know from the information given at the beginning of the problem that that number of moles of acid was contained in 50 milliliters of the solution. So we have the two units, moles from here, liters from the information given in the problem. We're ready to solve for molarity. So we will have 0.0148 mole over 0.0500 liters. 50 milliliters converted into liters, and we now have moles over liters, which is molarity. So now dividing by 0.05, and we have a molarity then equal to 0.295 capital M for the arsenic acid. Now we didn't do too well on the second exam relative to solutions. I would encourage you, if you didn't do too well in that particular exam on solutions, that you go back and think a little bit about these two steps here and what molarity means. Be sure that you understand those, because whenever we're doing solution stoichiometry, those factors come in. We need to know what molarity is if we're going to use it in solving the problem. All right, well, let's look at another example here. This one is just a little different. This time what we're going to do is we're going to start with a solid base. We're going to start with a certain number of grams of sodium hydroxide. we find that it takes 25 milliliters of phosphoric acid to react with it. And what we want to know is, what is the molarity of the phosphoric acid? Well, again, if we concentrate here first of all, then what we're saying is that to get an answer, we need to know what? We need to know the number of moles of phosphoric acid, and we need to know what liters of solution. We already have the number of liters of solution. So our first two steps is to get us to moles of phosphoric acid. Again, we do it 3 steps. The first step is going to be to determine the number of moles of NaOH. This time, however, we're not working with a solution of sodium hydroxide, we're working with a solid. And we know that 1 mole of a solid is equal to its molar mass. So we have 0.772 grams of sodium hydroxide multiplied by 1 mole of sodium hydroxide over the number of grams, its molar mass. If we add it up, we have 22.99, 16, and 1.01. So let's see, we have 23, 24, and 16. So we have 40.00 grams for the molar mass of sodium hydroxide. So step number 1 is to solve for the number of moles of known. 0.772 divided by 40, and we have 0.0193 moles of NaOH. Step number 2 is to find the number of moles of the unknown, which is phosphoric acid. So we're now going to ask, how many moles of phosphoric acid did we then have in the reaction? We have 0.0193 moles of NaOH multiplied by 1 mole of phosphoric acid per 3 moles of sodium hydroxide. So we see that moles of sodium hydroxide cancel, and we're ready to make our calculation. So we divide by 3, and we have 6.4 times 10 to the, actually we can have 3 significant figures, 6.43 times 10 to the minus 3 moles of phosphoric acid. Now, our question was the molarity, and we said that to solve for the molarity, if we know the number of moles and divided by the volume in liters, we've got molarity. Well, we've just solved for the number of moles. We know what volume it was in. We can now calculate the molarity. So the final step, molarity is equal to 6.43 times 10 to the minus 3 moles, all divided by 0.0250 liters. Notice that we have units of moles per liter, which is correct for molarity. And so our final answer, our molarity of the phosphoric acid then, is 0.257 capital M. Any question on any step of that? I know it's a lot of repetition that I keep saying, follow the 3 steps, follow the 3 steps, follow the 3 steps. The stoichiometry part of the previous exam was quite good. The solution part of the previous was not too good. So now we have to pull the 2 together. The technique was there, but it was using the solution information that was apparently the trouble. So I'm hoping by going through several examples here that, again, we get a better feel for working with these solutions. A third example. This time, we have a known amount of sulfuric acid, 150 milliliters. We have a known concentration of sulfuric acid. We know what concentration of base we're going to use. What we're wondering this time is how many milliliters, what volume of potassium hydroxide would I need to add to neutralize the sulfuric acid that I have in that other sample. My known is this, my unknown is this. Again, first step is going to be to determine the number of moles of known substance, which in this case is the sulfuric acid. That's going to be equal to volume in liters, 0.1500 liters, multiplied by the concentration in moles per liter, 0.986 mole of H2SO4 per liter, so our liters cancel, and the number of moles of sulfuric acid then, 0.986 times 0.15 gives us 0.148 moles of sulfuric acid. Same old thing, step number 2, how many moles of the unknown substance, which in this case is KOH, so we have 0.148 mole of sulfuric acid multiplied by 2 moles of KOH per 1 mole of H2SO4. Second step always involves that stoichiometric relationship from the balanced equation. And so now we have then 0.296 moles of KOH. Now the final step in this case asks us to determine the volume. We already know the molarity. We know that molarity is expressed in units of what? Moles over liters. But we can also write it, can we not, as liter over moles. Remember, any conversion factor, any relationship can be put either way. So what I'm going to do here is I'm going to ask the question first then, how many liters of KOH, and then we'll convert it to milliliters. We know that we need 0.296 moles of KOH. And we know from the concentration that 1 liter of KOH solution contains 0.686 moles of KOH. So those are going to cancel out, and we're going to be left with liters. So dividing now by 0.686, we have 0.431 liters. The question specifically was how many milliliters, and of course then the final would be to convert to milliliters, so milliliters would be equal to 4.31 times 10 to the second milliliters. Any questions on any step of that one? One final example. This one is representative of another experiment that you'll be doing in lab if you're in the laboratory part of the course. We've talked about calculating empirical formulas, and then if we had the information of molar mass, we could determine the molecular formula. And as a matter of fact, we've now looked at one way which dealt with freezing point depression, or boiling point elevation could be used to determine the molar mass of a compound. We can also determine molar mass of an acid or a base by carrying out an acid-base titration. And this is representative then of that. Here's the information given in the problem. We're starting with an acid. It says it's a monoprotanoic. That means that it contains only 1 hydrogen. All right? If it contained 2, of course, we'd have a different stoichiometric ratio. We're starting with 2.508 grams of the acid. put it into water, and we titrated it with sodium hydroxide, and we found that it took 29.54 milliliters of 1.063 molar sodium hydroxide to react it. We want to calculate the molar mass of the HA, which means that we're going to have grams of HA over moles of HA. Now, if we look at that, and that's the way we kind of want to approach the problems so that we know where we're going, we already see that we know how many grams of acid we had. It was given in the problem. So what is it we need to find? We need to find how many moles of acid that was. And we know that seeing it, we're talking about a titration process. Once again, I can find the number of moles of known. I can use my equation to find the number of moles of unknown, and I can then calculate the number or calculate the molar mass, okay, because we already have the grams. So actually we're going to go moles, moles, plug it in, and determine molar mass. So the first step, once again, moles of NaOH, which is our known. Volume in liters, 0.2954 liters multiplied by 1.063 mole of NaOH per 1 liter. So the liters cancel. So working that step, we have then 0.02954. Whoops, left a number on there. 0.02954 times 1.063. And we have 0.0314 mole NaOH. We then would ask, how many moles of HA do we have? Now we go back to our balanced equation. 0.0314 mole of NaOH multiplied by 1 mole of HA divided by 1 mole of NaOH. And you might say, well, what a stupid step to take. I mean, why would we bother multiplying by 1 over 1? Well, the only reason is to keep track of units and to make sure that we've put in that stoichiometric ratio. That has to be involved in our calculation. That's always in the step. And yes, it's just 1, but at least when we do it, we know that we have included step number 2, and we now have put things in proper units, which are moles of HA. Third step then, whatever it is that we want to solve for, we do. And in this case, what we want to solve for is the molar mass. So the molar mass, I'll just abbreviate as MM, is equal to the number of grams of acid, 2.508 grams of HA, divided by the number of moles of the acid, which we just calculated. I didn't quite finish that out, 0.0314 mole of HA, 0.0314 mole of HA. We look at the units, we have grams over moles, which of course is correct for molar mass, and we carry out the final step then. So 2.508, and we have a molar mass for this compound of 79.9 grams per mole. So, if we had a compound and we knew that it was either an acid or a base, and we wanted to determine its chemical formula, then first of all we would have to know the percent composition, so we could do an empirical formula. We could carry out an acid-base titration, which allows us now to determine a molar mass. And with the percent composition and an empirical formula and the molar mass, of course we can go to the final step, which is to determine the actual formula of the chemical compound. So here's another way in which we can determine molecular weights, molar masses, to use in determining chemical formulas. Freezing point depression, that was one of the techniques that we've talked about. Now acid-base titration. We're also going to look in a later chapter about using the pressure and volume if the material can be put into a gaseous state as a way of determining molar mass. So this then concludes what we want to say about acids and bases in this chapter. Again, I think that you really do need to spend a fair amount of time on this type of problem, looking carefully at the solution part of it to make sure that you understand the unit relationships as we go along. In our next lecture, we're going to begin looking at trying to understand why things chemically combine. Why is a material a proton donor or a proton acceptor? Why is it an acid or a base? We're going to begin looking at atomic structure, molecular structure, to be able to explain some of these things that we've talked about through the first 5 chapters.